So the topics is about health hazards posed by ionizing radiation. Is a little bit a different talk, but here is the human as an extremophile. This work wouldn't be presented here without, so this is work in collaboration with Susan McKenna-Lawlor of the University of Minot in Ireland, and Agata Wacka is my PhD student, which joined later. Well, I will first introduce the subject, then I will give some data concerning dosimetry, then I will speak about what it is known using statistical methods about possible deterministic effects and also stochastic effects due to ionizing radiation in missions beyond the low Earth orbits, or BLEO. So, well, just as a first introduction, there is a increasing interest in space. This is a list, I hope complete, of the countries that have launch capabilities indigenous. And of course, in boldface are listed the countries that have been able to send in space manned missions, and only the United States has sent crew beyond the low Earth orbit, so to the moon. And there are many applications of space industry. Among others, I would like to stress the importance of the monitoring of the solar activity, because the sun can, for instance, disturb the communications on the Earth. And well, if you want to have a clue if some topic is important, you can look where the money is flowing to. And so many private capitals, many private industries have joined the effort in space technologies. I just would like to mention SpaceX that very recently has made a record by sending a rocket on the space and then landing on a platform in the ocean for the first time. So of course, space exploration, especially manned space exploration, is costly. You can see here that if you want an exploration of Mars compared to what the missions, the Apollo missions made in the moon, well, the costs estimated are $2 trillion of US dollars. So this is slightly less than, so this is a factor 1,000, slightly less than a factor 1,000 more than the expenses of unmanned missions, like for instance, James Webb Telescope. Of course, in my opinion, this exploration of the space and also the settlement on planets or satellites outside the Earth, well, is an important step in human civilization. And on the other side, you can see what are the costs of other human activity, which are less positive, like for instance, war. These are the costs of the war in Iraq, which are comparable to those of exploring Mars. And of course, even during peace periods, there is the warfare that have quite high costs. So now some useful concepts. A low Earth orbit, LEO, is an orbit which extends from 200 kilometers to 2,000 kilometers. And what is important here to stress in the case of missions beyond the low Earth orbit is that the crew, unfortunately, will no longer be protected in such kind of missions by the terrestrial magnetic field. So, in particular, it will be exposed to radiation coming from the sun. And here, this is a short name for solar energetic particle, and energetic particle events, like for instance solar flares, are able to send enormous amount of energy to the Earth. And of course, there are cosmic rays. Cosmic rays are mainly of galactic origin. Now, a few concepts about dosimetry. Well, we have radiation. Radiation is delivering energy to some target. So, and this energy can be measured. And this is what it is, the concept of the absorbed dose. So this is the energy of unit mass, per unit of mass deposited by ionizing radiation in some target. And the units is the gray. Of course, there are many kinds of radiations. That means that different particles can ionize matter. And so the effects, for instance, of photons are much less important than the effects of heavy ions. And for this reason, well, it is very simple. The same dose, absorbed dose, which just count energy, can make more or less damages depending on the kind of particles. And this kind of damage, this enhanced ability of heavy ions to, sorry, I have this, of heavy ions to make more damage is expressed here by the so-called quality factor, which is a dimensionless factor which says that if the energy deposited is d, how much more or less the damage is, so how much is actually the effective dose that one received concerning damages. These are just concepts which are approximated and just valid for humans and for induction of tumors. The unit of the equivalent dose is 1 sievert, even if it is the same, because Q is a dimensionless parameter that the gray. But there is historically this different name. So we go beyond the low Earth orbits, and then we have problems because there are cosmic rays and solar particles, and this is the bigger obstacle in the case of exploration beyond in BLEO. So I don't expect you to believe that Lithuania is beyond the low Earth orbit. This is just for comparison. Here we went here, and the dose rate is quite is relatively high because it's 95 nanogray per hours. However, so this is outdoors. The annual, so indoors is even worse. So the annual absorbed dose is 0.8 milligray. You can compare here the absorbed dose rate on the moon, which is 10 times, it's 100 times, sorry, higher. This is 10 microgray per hours. So this is very high. However, what it says today is that the Apollo missions were lasting not so much, about 10 days. So at the end, the doses were quite reasonable, so 2.4 milligray, so in any case not bigger than 10 milligray for the whole mission. In Mars, on Mars, the situation, so if you want to travel to Mars, the situation is more difficult, and I would like to skip these details and arrive to the result that it doesn't depend how much you stay on Mars. The problem is the travel, because these are two different cases. Here above, there is the case of a longer mission, below of a shorter mission of just 30 days. In any case, you find here an equivalent dose which is about 1 sievert. So it's very high. Is that safe or not? So the answer is no. If you have a suicidal, if you want to send a suicidal mission to Mars, but of course, if you don't want to do that, there are some ethical principles which can be summarized like that. So first of all, the health of the crew and their progeny cannot be endangered by short and long-term effects. So here, deterministic effects are caused by cell killing. After the dose trespasses some threshold level, many cells have been killed and organs stops to work properly. Instead, long-term effects are stochastic. So there are damages that not always the repair systems of the cell is able to repair, and this can cause mutations leading to cancer or to genetic instabilities that are transferred to the progeny. And the second principle is that all factors that can disrupt the course of a mission must be predicted and eliminated as far as possible. So here is an example of the NASA career effective dose limits for the entire career, but imagining for that the total time that the mission is no longer than 1 year. And you see here it depends on age, it depends on gender, and here the levels, the values are quite high. But anyway, there are always this principle. First of all, this deterministic effect should have a low probability, less of the risk should be less than 1 by 1,000. And the exposure to radiation, if it concerns this stochastic effects, tumor induction, should be such that the dose doesn't endanger too much the astronauts. So just no more than a 3% risk of exposure-induced death from fatal cancer with a confidence level which is quite high, so at least 95%. So these are based, these recommendations are based from these reports of the National Council of Radiation Protection, and other data can be found in our publications concerning, for instance, the recommendations, the regulation of other in other countries. So deterministic effects. These are, I already explained what they are, and here the situation is such that so we can, for instance, compute using statistical models what happens, and this is the risk that there will be some effect like vomiting, but also more serious like destruction of the blood-forming organs in the spine. And as you see here, there is a threshold that is triggered, and of course this threshold is depending on various parameters that have been computed statistically, and that the result here is that we can be quite safe, because this is the risk of this blood destruction of the blood forming cells, of the blood forming so of the it's called this bone marrow, and which is forming the blood cells. These are relative, they are very, the risk to have such disease damage is very low. However, there are many buts here, because first of all, we use models, and in particular models based on the bombing in Hiroshima and Nagasaki. For instance, now that there is Chernobyl, this is now the anniversary of the Chernobyl accident, and Chernobyl is not in agreement with the data of Chernobyl are not in agreement with Hiroshima and Nagasaki. So and the problem is here that the quality factor corresponding to some percentage of gamma radiation and neutrons is 1.09. Interspace is 3 or more. So these are different radiation, and it is very difficult to estimate the damage made by these heavy ions radiation. So these are HZE are the high atomic high atomic number energetic ions that are very dangerous. For instance, there is one very well-known shortcoming that are light flashes that the astronauts have during the space mission, for instance, Apollo space missions, and these are related to ionizing radiation. The mechanism is not known, and they can disturb the sleep. Okay, thank you. Then there are changes in even more dangerous are changes in neurons and synapses due to the destruction made by such ions. And so for concerning heritable effects, this is now very well known concerning these low lead radiation, so photons, electrons, but high lead radiation is not well understood what is doing about this transfer of genetic disease to the children and to the progeny. So I would like to finish these results by, for instance, computing the stochastic effects using models. For instance, we can compute the number of cancer mutations. So here an event is a cancer mutation caused by one double-strand break, which is you have two pieces of DNA. When there is the radiation, you have one piece of DNA. You have radiation; they are cut into two. So we can provide, using these models, a very good estimation of this number. From that, one can find, for instance, what is the probability of inducing cancers having a given dose. And this is an astonishing experiment that is working and started a new technique for counting the double-strand break due to radiation. So let me conclude. First of all, cosmic rays contain these high zeta particles, ions, whose effects on health are not fully understood. So it is very dangerous. They can destroy the brain. So, well, it's very complicated. The doses for going to Mars are quite high. And, these ethical principles are certainly not fulfilled. And there are difficulties to estimate the long-term risks of exposure that are so long. So because one mission to Mars lasts 400 days, usually you have much less. So these models are based on Hiroshima bombing. So the contamination were just lasting 10 minutes or more, but no much more. And then, I want to finish here saying that, no one of the protection limits utilized so far considers the fact that astronauts are living in a very dangerous environment with, for instance, low gravity and bacteria and complicated psychological situation which lowers the immune system. So thank you very much for your attention.